So, welcome to lecture number 12, I believe it is, in the introduction to Lattice-Boltzmann method. And today we have a kind of an advanced topic, so we'll have only 3 more lectures. And in these 3 more lectures, we look at things that, going deeper into the detail. Maybe you already had the impression that we are sometimes deep in the detail, but today we have the topic of grid refinement in the context of Lattice-Boltzmann. So we all know Lattice-Boltzmann is a Cartesian grid method, so you always have the same resolution, and this may not be always what you want to have. So, because actually Lattice-Boltzmann, LBM, is often used for external flows. Actually, it's mostly used for external flows because what Lattice-Boltzmann practically is most used for is to calculate the drag coefficient of cars. I mean, if you ask what is Lattice-Boltzmann mostly used for in the world, then it's the computation of drag coefficients in cars, I believe. And in particular, this has been so for more than about 30 years. So for 30 years, Lattice-Boltzmann, especially, there's this company PowerFlow that from the late 20th century actually was using the Lattice-Boltzmann method in automotive industry in the automotive industry and to compute the drag coefficients. So if you think about this particular problem, but also similar problems, so you have you have a car. Now let me approximate a car that's potentially on a road, and you assume that there is, we simplify things and say there's wind, but of course the car is driving. It's usually the opposite way. So, and you put the car into a box because you want to know what is its drag. So now you should know that dissipation, which is responsible for the drag to a large amount, this happens in the thin boundary layer on the surface of the object. So thin, with thin, we often mean it's really thin, like a millimeter or even less, for an object that may be very large, say it's a car, or it may be a cargo ship, Now you have a cargo ship, and the surface where you have the dissipation is just, the surface directly around your car. So then maybe on top of this, so okay, the way I draw this is of course a little bit nonsense. You would have, let me say, you get a little bit more behind and a little bit less in front, typically, saying that there is little happening in with regard to the flow in front of the car, but there is more happening behind the car. Now your problem is, what you would then like to do is to use say, okay, let me see, you have a high resolution here at the car, So at the same time, Well, you need a high resolution here. There is not much dynamics far from the boundary layer. So the idea is, if there's not a lot happening, then you don't need a lot of computational resources. Yeah? So let's say a low resolution is sufficient. And therefore we'll have here low resolution. Or let's say we would like to have low resolution. Yeah? We'll have high resolution close to the car and potentially in the wake of the car or whatever other objects, yeah? And we would have a low resolution far enough away from the thing. Yeah? Because, I mean, it's always mathematically possible and reasonable to say we'll resolve everything with the same resolution that we have for the boundary layer, yeah, and then we are fine. But just imagine how many cells and nodes you need for this. For example, I note that there are people potentially here in the audience that like to simulate wind farms, yeah. And now imagine you want to resolve your structure. There is a structure that you need to resolve inside or around this wind turbine, and then you'll want to place this wind farm in an environment that you study on the scale of tens of kilometers, yeah, in all directions. Then it's just not feasible to have one resolution. Okay, so for this reason, and in particular here, starting with the study of track coefficients of cars, there was grid refinement, and the first grid refinement that was used in Lattice Boltzmann, there's actually a patent on this, which is so old that I believe it's already run out. Yeah. So because I think there's a US patent from somewhere the middle of the start of the start of the 90s. So it's more than 25 years old. Yeah. So there's a volumetric grid refinement. I mean, it's really interesting that there can be a patent. I mean, there should not be patents on Lattice Boltzmann. There are lots of patents on Lattice Boltzmann, actually. But it's funny to think that the patents on Lattice Boltzmann are already 30 years old, yeah, or more. So this, by the way, the things that are patent in Lattice Boltzmann are not usually the best things. Yeah, so you find something better. So I just say that this was a popular. Yeah, popular is probably not in the sense that it was often implemented. It was actually only implemented by this one company. Okay, not completely true. There was also some works in academics, but this one company used this in particular already 30 years ago, and did this on staggered grids. We will talk about staggered grids later a little bit more. So suppose I place, let me see that I do this in a reasonable way. Suppose that I place my lattice nodes like here. Okay, I'll need a little bit more space today because I have to do a lot of drawings. So I call this a node. So maybe we've talked about this already, but there is always the distinction in Lattice Boltzmann, or when we analyze Lattice Boltzmann, the way we analyzed in this lecture, we used Lattice Boltzmann as a collocation method, meaning that we're talking about the state of the node. Yeah. Yeah, so this means this is the state, the velocity, the moments there give the velocity at this node. Yeah, so there is an alternative. This is an important thing when you do the asymptotic analysis, because then your assumption is this is the velocity at this point. Yeah, because otherwise you have a different Taylor expansion. Outside of mathematical analysis, there is an alternative interpretation that you could also use, but then you would need to have a different asymptotic expansion. Yeah, you could also see the moment as the average inside a control volume. Yeah, but this was not the way we interpreted this. But this is the way it is interpreted in this volumetric methods. Yeah. So because first of all you need to distinguish between is there cells or is there points. Yeah. So we always talk about points, and they talk about cells, but they use the same method. It's the same interpretation. It's the same method with different interpretation. Yes.
The difference would be just 1/2, right, in the Taylor expansion, or we would need
no, the interesting thing is if you do the Taylor expansion and you go to the middle, then you would find that these two interpretations are the same to second order. Yeah, so that's in the end of the day you can use both interpretations are legal as long as you are not talking about going anywhere higher order than second order. Yeah. So, but if you try to extend the interpretation to what is going on with the error, then it's no longer the case. Yeah. So okay, we interpret things as cells, and this means we say that this here is a cell, and we call this now a coarse cell because we say this is the this is the coarse grid that we interpret. So here's a coarse cell. Yeah. So the interpretation is that the moments that we calculate for this point here are the average of velocity and density within this cell. Yeah. So when you have this, then you can split this cell up into, if we are in 2D, we can split this up into 4 more cells and call this green one here a fine cell. So, and now inside this patent, they write this like this. They call this operation an explosion. An explosion operation where, let me see, say we interpret this here as the populations of a coarse cell, say this is coarse, they put this into, so by the way, this is not the velocity that we scale, this is the space that we scale. So they just put this into 2D, of course, otherwise in 3D in 8. They just split up these populations So, and they do something very, very simple, namely they say that we have Fij fine is equal to Fij cos divided by 4, of course in 2D, otherwise divided by 8. Yeah? So they take the population, divide them by 4, and set the same population everywhere within the cell. So all of them, so the important thing here is that all of them have, after this explosion, all of them have the same populations. Yeah, so there's no distinction. Yeah? So this is matched in with something that they call collapse. So I may have to draw all of this again. I don't know whether I waste some time. Okay, I'm not putting the arrowheads now. Yeah, so this is, say we have a fine cell. No, we have 4 fine cells, and we put this into one. Oops. Okay, not very beautiful now. Into one cause cell. So what they do with Fij, the cause population, is simply the sum over, in this case we are in 2 dimensions, so there would be 4. They simply sum these things up. Fij fine over the 4 different populations, cells in this case that we have. And this operation here is called collapse. So, and on top of this, we are using acoustic scaling. Acoustic scaling means delta x by delta t is a constant, meaning that delta xc is twice delta x fine, and delta t c is twice delta t fine. And by the way, this is now this is something that you have to appreciate as a difference between between the Lattice-Boltzmann method and almost every other numerical method out there. Yeah, so usually, okay, it is very common that numerical methods, finite elements, control volume, whatever, use grid refinement, have locally finer grids than somewhere else. Yeah, so this is very common. Even more common than, and it's potentially simpler as in Lattice-Boltzmann. So, but what almost all of these methods have in common is that they always use a common time step. Yeah, so they never distinguish between the time step in the fine regions and the time step in the coarse regions. What you will almost always in Lattice-Boltzmann, there are a few exceptions. Actually, I'm also on the paper where there was an exception to this. It was not my idea, but anyway. With a very few exceptions in Lattice-Boltzmann, it's usually the way that if you have a finer grid, then you have a finer time step there. Yeah? So the thing is, the time is not running synchronous. You are not solving the entire system with all the same time steps, but you have a causal time step on the coarse grid and the fine time step on a fine grid. This has advantages and disadvantages. Okay, so why so? So why are we using acoustic scaling? I mean, Manfred Kraftschick will probably tell you that we use acoustic scaling for efficiency, which is one reason, yeah. But I mean, like, if you can have a longer time step on the coarse grid, why not? Yeah. Yeah, but there is actually a physical reason for acoustic scaling. And here I take now the freedom to just paste something that I have prepared. Okay, sorry if you wanted to draw this now. I'm going to explain. I found this, when I draw this, I always mess it up. So depending from what, oh, somebody raised the hand? As we are using acoustic, does it mean omega will also change in the final grid? This is correct, yes. I will talk about this later. Yeah, but this is correct. Okay, so first, why in this in the first place? So depending on where you come from in the world, you'll have a different name for what the French call Descartes' law and what the English call Snell's law. I don't know. So you'll probably be familiar with light scattering in, not scattering, bending is the right word. When they hit a surface, a transparent surface. So, for example, you can see your reflection in a window. Yeah. So, even though the window is transparent. So the reason why you see the reflection in the window is because the speed of light inside the window, inside the glass, is slower than in the air. Yeah? So, and whenever this is the case, that the speed of the wave speed in a medium, whether this is a sound wave or a light wave, yeah? If they do not match up and there is an interface, then at this interface, there is, according to Snell's law or Descartes' law, yeah, there will the angle of incidence will be bended, yeah, and under certain angle it will also come back, yeah. So this means whenever you have two domains with an interface in between, and you try to pass waves from one into the other, then there will be a reflection. Yeah? So, now for lattice Boltzmann, this means if you have two grids of different resolution or whatever, two domains in which the speed of sound would be different, then you would have a reflection on that interface. So this is something that you want to avoid because this is completely artificial. Yeah? So the way you can avoid this is having the same speed of sound in both domains. Now we have a little bit of problem in lattice Boltzmann in that way that our speed of sound is dictated by the lattice. Yeah, we discovered that because we have only, in 2D, for example, we have only 9 speeds, yeah, and we are missing some of these third-order moments, we can get away with missing these third-order moments if we take a specific speed of sound with respect to, the speed of sound square root 1 over 3 delta x by delta t, yeah? So, but we have to keep this constant, yeah? And now if we change delta x and we need to have this constant in order to run lattice Boltzmann, we have to change delta t accordingly, yeah? So this is the reason why we use acoustic scaling, yeah? So, as I was just saying, that our speed of sound is 1 over square root 1 over 3 delta t by delta x by delta t. So, and now when we use acoustic scaling, we have no breaking No breaking of sound waves. So this is the motivation why we use acoustic scaling here. You may have other motivations to do it in a different way, yeah. But with this method, you can actually also simulate aeroacoustics. Yeah? We simulated, in particular, sometimes when you use aeroacoustics, you need many layers of grid refinement. Actually, the one simulation where I saw the most layers of grid refinement, I think it was 11, yeah, was an acoustic simulation of an organ pipe. Yeah? Because you have to, in acoustic simulations, you have to see actually simulate the generation of the sound, yeah, which is usually in a very, very tiny place, and then you have to, find the propagation into a big room, yeah. So usually this is an application of grid refinement, and grid refinement, I mean, a lot of grid refinement, like, if when you have 10 layers of grid refinement and you double the resolution all the time, yeah, so then the largest cell is 1024 times as large as the smallest. Yeah, so 11 layers means there was 2000 over 2. The ratio of the resolution was over 2000. Yeah. So, and there you don't want, obviously, you don't want to have reflections on all these 10 interfaces. Okay, I'm talking too much. Okay, let's just write these things down for the record. So acoustic scaling at grid interfaces. So this avoids reflections, and yeah, so according to the question from the audience, we have to rescaling of relaxation rates. And the non-equilibrium populations. By the way, according to the old methods, this was not done. They did not rescale the non-equilibrium populations. They just didn't. Even though you would say this is potentially wrong. Yeah, we know that this is wrong and causes problems. But they were industry. They just did it. I mean, they just omitted this. Okay, coming to this particular question of the rescaling of the, yes.
Sorry. So if we have different if we have different scales or different meshes inside one, does that mean that and it depends on dt. If we use diffusive, would it mean that the viscosity also would be different in
No, you mean if we use diffusive scaling in the grid refinement?
Yes.
Then then the viscosity would if we used diffusive scaling in grid refinement, then we could keep the relaxation rates constant. Okay. Yeah. But this one consequence, I mean, of diffusive scaling would be, if you think about it, or I give you as a homework to think about it, it would be that we need that when we double the resolution, the resolution, we will have to quadruple the time step. Mm-hmm. Yeah.
Okay.
So so we wanted to talk about the relaxation rate scaling. Yeah, this was the question that just came up. relaxation rate scaling. So we know viscosity is our physical parameter. Viscosity here given as nu, so kinematic viscosity, is theta. Theta is the square, the square of the speed of sound without units here. 1 over omega, so this is the omega of the BGK, 1 over omega minus 1/2 delta x squared by delta t. So if you want to pass the exam, you know this equation, right? Yeah. So if this is the case, then we have for the cos, omega cos 1 minus 1/2 delta x cos squared divided by delta t. Cos must be omega, so the viscosity has always be the same. Yeah, so it's 1 over omega fine minus 1/2, and here comes the delta x fine square by delta t fine. So what we want to know, suppose omega c is given, then we want to know what is omega f. I'll write 1 over omega f because this is just a little simpler, and see that if we transform this, we get to delta xc squared divided by delta t square times delta t. Oh, I'm messing up. Delta t fine divided by delta x fine square 1 over omega cos minus 1/2 plus 1/2. So these things, this here, when we double the resolution, so this is the assumption, we are doubling the resolution, that means that this here turns out to be 2. Yeah? This turns out to be 2, and therefore 1 over omega f is equal to 2 over omega c minus 1/2. So we have to use different relaxation rate in the two different grids. To keep the viscosity constant, yes. So in this way, we have now the speed of sound constant and the viscosity constant. Yeah? Okay, let's rub things a little bit up with regard to this volumetric refinement. Okay, let's say something positive first. And so this conserves mass and momentum. And I believe it is the only grid refinement method that actually around that does this. Yeah? That actually conserves mass and momentum. And you know, you will always find people saying, so this is the most important thing, conserving mass and momentum. Yeah? But this doesn't, I mean, conserving mass and momentum it's pretty simple to conserve mass and momentum. Yeah? Because there are very simple and very wrong methods that conserve mass and momentum. And there are very good methods that are actually not conservative. One particular method that is very, very often used in engineering, in which is not conservative, is the finite element method. So if you really believe in conservative methods, you cannot use the finite element method, yeah. But the finite element method is a very successful method, yeah, in engineering and mathematics, yeah. But it's not conservative. Yeah, so not meaning politically. Also, yeah, don't always think you have to be conservative. So why because they have one advantage, and otherwise they only have disadvantage, or not only, but mostly disadvantages. So, for example, now they are conservatives, but they are not continuous. Yeah, so they are discontinuous in pressure and stress. Okay, it's a little bit challenging to prove and show why this actually is the case, but just believe me now. The other thing is that this, so this can be good or bad. Good or bad, it's highly dissipative. Okay, is it good that something is highly dissipative or bad? Usually it means that you are not accurate if you're dissipative means that it dissipates signals that would physically not be dissipated. Yeah? Yeah, so it's not physically dissipation, it's not physical dissipation, but it's a dissipation of the method. And you can always argue that dissipation is not so bad because what dissipation does is stabilizing your method. So if you have a dissipative method, then usually this is a stable method. And this is also the reason why this is in a code from a company, because they are selling the stuff, and you can always sell something that is stable. Yeah? Even if it may not be accurate. So why is this the case? The problem here is that I need a little bit more space, that this explosion method is zero. Zero means inconsistent order interpolation. So we call this next neighbor interpolation. Yeah? So it's just you saying, you measure the temperature in Hanover, yeah, and you ask what is the temperature in Braunschweig, then you simply say, oh, it's the same. Yeah? The next neighbor interpolation. Yeah? So we'll all get the same. This is as we're going to see, not sufficient. So because let's look at our Navier-Stokes equation. What interpolation? So suppose we want to suppose we want to solve the Navier-Stokes equation. Yeah. So looking at the Navier-Stokes equation, and in the most simple way I can write it. So say zero order of pressure. Now this is the dt is now supposed to be the advective derivative, so a little bit simplified. Here is equal to minus theta, the second order of rho, plus the gradient of rho plus rho zero viscosity, and here we get Laplace operator, so the second derivative of velocity, right? So in order to fulfill this equation, we need to be able to reproduce a gradient in density, yeah, and a second derivative in velocity. Otherwise, we are not representing this equation correctly. Yeah. So so suppose there originally was a gradient in density or whatever, and you just do next neighbor interpolation. This means you say that two neighboring nodes have the same value, right? So, and if they have the same value and they try to compute the gradient, they will always say the gradient is zero. Yeah? So for this here, so there's a first derivative. There's a first derivative, And the minimal way you need to know your density field is by linear interpolation. Otherwise, you cannot reproduce the gradient of the density. Here, for the velocity, we have a second derivative. So in order to actually get a second derivative, so if you have just a linear interpolation, yeah, so we take two derivatives, it will always turn out to be 0. Yeah? So in order to represent this in the first place, we need to have at least quadratic interpolation. So this is the minimum required. And this volumetric method does neither. Yeah, so it conserves mass and momentum, but it will not, so it causes, so this will cause discontinuities in these two terms, which are very visible in your results.
Here I have a question.
Yes.
Because we, for example, we have considering the density constant. So wouldn't this term of...
Okay, no. The density constants. I don't know where this is the background density. This is the variation in the density second order. This is not constant. This is basically the pressure.
Okay.
Yeah.
Okay, now I understand. Thank you.
So now we need some interpolation methods. This is the alternative. Also, by now, the only method that is actually used. I mean, you will always find some people. I mean, this is also, I noticed with, I have to say, some of you, yeah, that you sometimes look into the old books and dig up old stuff. And I mean, it's okay, but you should know that there's often reasons why these things are no longer done. Yeah. For example, one big example is this Su-Her boundary condition. Yeah, so this is very often done in some classroom examples. Yeah, that they use this, but in practice, in the real world, these things are no longer in use because they come out of fashion because they don't work properly. And one thing that doesn't work properly is the volumetric grid refinement. So, but also in interpolation, there are classical and more modern versions. There are actually a lot of different versions. Scientists always have to invent something new, otherwise they cannot publish. So, classical interpolation with overlapping grids. So there's no volumetric interpretation now here required. We are back to our old picture of the nodes. So let me see that I draw this something. So by the way, this is you will now benefit from these lines on your paper if you have them. Okay, say we'll put nodes. Oh, I completely messed up. Sorry. Don't follow me. Don't follow me. So I need to. I mean, you should have noticed. Yeah, this should be a Cartesian grid. So, sorry. Did you do it the same way?
Yes.
So, say on the left is the cause, and on the right is the find, right? So, say we'll have. Okay, I should have used as a color. So, say here is an overlap, and of course we also have these nodes. These nodes here. So this node here are nodes requiring interpolation in space.
That is where the grid.
Yeah, so this is what we call a hanging node. This is they're not matching. Yeah. So by the way, one thing that you always have to remember, due to this delta t cos is twice delta t fine, you also have to have a temporal interpolation in this on this grids. Temporal. So temporal interpolation is required not only for these nodes, but also for these nodes. Yeah, so these nodes also need temporal interpolation when they go to the fine grid. This here, that actually have no overlap. Yeah, that the nodes that are on both sides. Okay, now how do we do this data transfer? Between resolutions. So what is typically done, I mean, there are many different methods that there are variations that sometimes do it a little bit differently, but say common way is to split the pre-collision distribution in an equilibrium part and a non-equilibrium part. I mean, there's also the option to do it in another way, which I believe is wrong, but there are other people that insist on a different point of view, but it's always like this in science. So say we have Fij is Fij equilibrium plus Fij non-equilibrium. So now there are two things to what am I writing? I want to write about the Taylor expansion. So Taylor expansion as a simplification of the asymptotic expansion. So we just Taylor expand MAB without asymptotically expanding it. Yeah. So just saying MAB is MAB the equilibrium minus delta x divided by omega, and here comes dxma plus 1 b plus dy ma b plus 1. So this is the same as the asymptotic expansion, just we do not expand the moments themselves. Yeah. So and then if we don't do this, we have of course to say that this here goes on with second order. So and this here, this is of course the non-equilibrium of the moment. And one reason why you want to okay, so one particular reason is this thing here has to be scaled. So you cannot just interpolate the populations because you need to scale this thing here. Yeah? So then you first need to take this out, scale it, and then you can interpolate this. So the other thing that I don't want to talk too much about, but you can think about it this way. So the equilibrium part, if you remember that the equilibrium in lattice Boltzmann is usually a second order or higher polynomial in velocity, yeah?
Yes.
Yeah? So now you have a choice between, you could simply interpolate this equilibrium part, then you are interpolating a second order polynomial, or you could actually interpolate the velocities and recalculate the equilibrium.
Okay.
Yeah? So now what would you think is more accurate? Or what would be the difference?
Well, if we get the velocity and then get the moment, like the error would also go to the moments, right? So I would say that the other.
The other. So what would you prefer?
So
Would you interpolate the equilibrium, or would you interpolate the macroscopic, I mean, the velocity, and then calculate the equilibrium?
I would interpolate the equilibrium.
Okay. Then you would have. Okay. So there is a signal processing reason why you would be wrong with doing that.
Okay.
Yeah. And the thing is, if you interpolate, you know, if you have high frequency, and this is a problem we're coming later to. Yeah. So if you have a high frequency signal, and you're taking the square of this, you have double the frequency, right?
Yes.
So, interpolating something that is double the frequency is more difficult than having a lower frequency. Yeah?
Okay.
Yeah? So, you, with your interpolation of the equilibrium, you would have killed your performance in high Reynolds number flows, yeah, So you would generate spurious waves there, and you would spend the rest of your PhD thesis or whatever trying to find out what went wrong, yeah. So if you interpolate instead the velocities, and you take the square later, you have escaped this doubling of the frequencies. Okay, so a little bit tricky everything here. Yeah. Okay. Sorry for we are taking too much time, but it's interesting topic. Okay, so we'll have to do the reconstruction of Fij on the fine grid. Write it this way. Is Fij equilibrium plus delta x fine by omega fine omega cos by delta x. So these things are of course just factors of 2 C non-equilibrium. So this is how you reconstruct the fine population from the coarse population, and the other way around. The coarse population is the equilibrium. So the equilibrium is of the fine, equilibrium of the coarse previously, and now equilibrium of the fine, plus delta x cos by omega cos omega fine by delta x fine f fine non-equilibrium. Okay, so these are the transformations. And all of this is done in pre-collision, which is also important. So the first example, when people tried this out, they did this in post-collision, which caused some problems. I mean, the good thing is if you always do it in a stupid way first, so that somebody else can write a paper and I found a much better version. I could just have done it right the first time. So we use we do the data transfer usually nowadays, not in the first papers, but nowadays in pre-collision, because as they found out that if you do it in post-collision, you have a singularity. So this doesn't work for, then the scaling would look a little bit different, and in this scaling you would divide by 0 if your omega would be 1. And this is, of course, something that you would want to avoid. So if you look in the very old papers by Philipp Popper and Hähnel, then they use post-collision, and they have this problem. Okay, we need to talk about how we interpolate these hanging nodes. Interpolation of hanging nodes. So hanging nodes is, in numerics, it's also is a common term that is also used for finite elements, for example. Say we have our two grids like this. So then we have overlapping nodes. These overlapping nodes are these here. And here we can just scale, right? We can just take the population from the other grid and scale it, right? So, and then we have the other ones that have no matching partner. These are these. So, and we'll call these guys, they are the hanging nodes. And these guys are the overlapping nodes. We have, at the overlapping nodes, we have to do temporal interpolation, but not spatial interpolation.
In overlapping nodes, we have to make spatial, but not, or could you?
No, in overlapping nodes, we do not need to interpolate in space, okay, but we have to interpolate in time, because they don't have the same time step. So the stencil, okay, I need a little bit space. Let me see. I put it around here. So say this is my hanging node, which I'm intending to interpolate. Then I will have, let me see, so I will have a node here, a coarse node here, and a coarse node there, and then the next coarse node will be there, and the next would be there, okay? So this thing here, this is the interpolation stencil. Need a bit of space. The interpolation stencil required. We want to do quadratic interpolation, as we said, but we need 4 nodes, which is more than you would usually need for quadratic interpolation. But the other thing is that you want to have the thing symmetric. So you can do quadratic interpolation with 3 points, but if you do this, then there is no way to put them symmetrically on both sides. Yeah? And this is not what you want. So this is why you need 4 points. So you see you have a relatively large stencil. Okay, so we have a little bit history lesson today. Yeah. So first they started off with the volumetric stuff. Then they used this overlapping interpolations. Yeah. So and this is actually something that some people. I mean, this is something that still in use, but not in the way that it was originally introduced. Yeah, so it had to change a little bit. The thing is, some people prefer to have this overlapping nodes because apparently they do not need, as I said, apparently require no interpolation. In space. I mean, this is the thing that I was telling you all the time now, right? I mean, in particular, they have no interpolation from fine to coarse. Right? So for every fine node, or every coarse node in the interface is matched by a fine node. Yeah? So then you apparently don't need to interpolate from the fine to the coarse grid. You only need to interpolate from the coarse to the fine.
From the coarse to the fine, okay, yes.
Yeah. So, but no way back. And this apparently is a good thing. Do you agree? If you can avoid, yeah?
Well, if we cannot, so if I understand right, we have coarse and we have fine. And apparently, the overlapping, meaning the ones that are in coarse and right, they do not need interpolation.
Yeah, they don't need interpolation. And this is a good thing. Okay.
Well, yes.
Okay.
Seems like it's a good thing.
It sounds like it's a good thing. Yeah. If you think, there's always things that sound good if you don't think a lot. If you think quick, but if you think longer for it, the longer you think about it, the worse they become. So this is originally considered an advantage. Of overlapping grids. Of overlapping over the staggered grids. So the staggered grids were the ones that we have been using in the volumetric case. So, I mean, and this is something that was also done here in this institute before I came, and then I had to tell them, guys, this is a big misunderstanding. And it was not easy to convince the civil engineers of this. Okay, I'm, by training, I'm a microsystem engineer, and we study signal processing. Yeah, anybody studied signal processing in their undergraduates? So if you study signal processing and you see this kind of grid refinement, I mean, even very small student that doesn't know, I mean, not high level anything, yeah, but just you remember your signal processing class and you see this kind of interfacing, you will immediately say this doesn't work. Yeah, because so for people in signal processing, it's very obvious that you cannot do this. Yeah, and let me just point something out. I have this here. So this is from a colleague of mine. So this is the way they did grid refinement in this institute when I came here. So this is, you see, this is not my picture, so I should say that this is copyright by Geller 2011. Yeah, so it's some time ago. So what you discover here? So they use grid refinement, so several layers of grids, and and they have turbulent flow, so there's high Reynolds number flow, right? And what you discover here is that at the interface you get this strange streaks. And you get these streaks when you go from the coarse to the fine.
Okay.
So there's something
Like leaking or going
so there's something going wrong here. So, and in order to see what is going wrong here, we have to go a little bit into data signal science, I would say. Data downsampling. So, even though you are apparently not data engineers, have you ever heard about the sampling theorem? Because this is something that people should have studied somewhere. Sampling theorem. That has different names. So we round the Shannon, Cloud Shannon.
the entropy of Shannon, information theory.
Yeah, so this Shannon, yeah, this is this guy. The Shannon sampling theorem. You see, this kind of no interpolation is breaking the Shannon theorem. Yeah. So the Shannon sampling theorem requires data to be band limited. At half the sampling frequency. To avoid aliasing. Aliasing, I never know how this is properly pronounced. So, I mean, more important than learning lattice Boltzmann is learning Fourier transform. Yeah, I hope everybody, I mean, if there was no reason for this, that because you don't understand lattice Boltzmann without Fourier transform. Yeah, Fourier transform is one of the most important things that you can learn in. I hope you kind of learned this a bit. Yes? Okay. Let's look at Fourier coefficients. Okay, let me write down a sentence. Consider the Fourier transform of discrete data points. Because this is what we have, yeah? Our data is on discrete points, yeah? So we have data on the coarse side and we have data on the fine side, and we want to match these two, yeah? So, and they don't have the same content of information. So on the fine side, we have more information than on the coarse side. And say this graph here now gives us the Fourier coefficients. The Fourier coefficients and the absolute value of them, because I don't want to draw sine and cosine in different ways. So absolute value means they will always, all of them will be now positive. Now I have to do a little bit like this. So, say FSF is the sampling frequency of the fine on the fine grid. Yeah? Then what we know from signal theory is that if we have coefficients in this range, and they will usually go down. I mean, this is what we hope. So there's a lot of signal in long waves and a little signal in very short waves. And we sample this stuff, then the Fourier spectrum will have a mirror image around its half frequency. So, it's not very beautiful drawn, but this is, say, the mirror image. Mirror data. Okay, so they are, why does this look so ugly? One, two, no, okay, so it's looking ugly because it is ugly. It should be, say, I did not put it in the right place. This would be F. SF. So it would end up here and would go up until here, right? So I messed a little bit with my plot. So it should have the same distance. Okay. Yeah? So this means that here is the half frequency. The FSF half, which by the way is, because we are halving the grid spacing, this is also the sampling frequency on the coarse grid. Yeah? So on the coarse grid we have the same thing. We have Fs coarse half here. Okay? And now we have a problem because this spectrum is mirrored. The spectrum is mirrored, and it's now mirrored around this line. This means that we'll have this thing here. Now, of course, it does not actually look like this, yeah, because these two things now overlap, yeah. So if they overlap, what you actually have is that inside this low frequency part, yeah, so this is the frequency that you see. So this is now the apparent signal. And this is what we mean by aliasing. So you have high frequency signal on your high resolution grid, yeah, and you try to transfer this onto a grid where these high frequencies do not exist, yeah. Okay. So, and what then happens is that these high frequencies are put into low frequencies. So you will generate a spurious signal from the high frequencies that you have not filtered out. Yeah? Mm-hmm. So all of this will work very fine. We'll have overtime again today. This will all work very fine if you, for example, have a laminar flow where you have no high frequency data, then you can do the transfer and you will probably be fine. Once you have turbulent flow, where you have all the high frequency part and you transfer this data directly just by sampling on a grid that has not sufficient resolution, so that does not have double the resolution of the finest signal. Yeah? It needs to have double the resolution of the finest signal, then it will produce a spurious signal in a different frequency. So this means you can only you could only do this if your signal would be well represented even on the coarse grid. Okay. Which is difficult to handle with turbulent flow, as you can imagine. Yeah?
That means that the overlapping nodes do need interpolation in space.
They do need something. Yeah? So say this is the sampling frequency on the fine grid, and FSC is the sampling frequency on the coarse grid. So, okay, let's still write everything down. Sampling produces spurious mirror image at the half F as the half sampling frequency, meaning that, what am I writing? Signals at frequencies larger than half the sampling frequency cannot be distinguished from lower frequencies. So this took very long for people to actually find out that there is this problem, and of course there's a solution to this. Namely, you can low-pass filter. You use a low-pass filter before you do the sampling, which in the sense is okay. So this is a solution to the problem. Yeah. So you said that, okay, I don't need interpolation. Then you produce a problem, and then you use an expensive solution to fix this, and then because if low-pass filter is at least as complicated as doing interpolation. Yeah. So you don't win anything by this. Okay. The other things that I've said that laminar flow is often naturally band limited, so that with laminar flow this may actually work without you thinking, which is dangerous, because if something works sometimes, you always have some hope that it is the right way. Yeah, so it's sometimes better that things don't work at all. Then in turbulent flow, which many people of us try to investigate, turbulent flow is band limited only by, if you have any idea in fluid dynamics, then you know that there's a so-called Kolmogorov length. And one over the Kolmogorov length, yeah, is the band limit of your turbulent flow. So there's a very short distance, very high frequency signal that you would have to deal with. So, and by the way, as I said in the beginning about the volumetric grid refinement, which I said was very dissipative, they never run into this problem. Yeah? They also didn't think about it, but they just don't have this problem. Yeah? And the reason why they don't have the problem is they don't have overlapping nodes. They never have overlapping nodes. The grids are staggered. Staggered means they are not overlapping. Yeah? They are always displaced against each other. So they always have to interpolate. And interpolation, usually most of the interpolation or the interpolations that they use, whether they thought about it or not, usually act as a low pass filter.
Okay.
Yeah? So you do interpolation. Interpolation is always is usually dissipative. Yeah? So it destroys part of your signal. Yeah? And therefore it will just get rid automatically of these higher frequencies. Yeah? So whether you think about it or not, but if you use staggered grids, you don't have this problem. I mean, the thing, so this is very long already in work. You see, the problem that we have a little bit with this is you can probably not write a lot of papers. This is what scientists want to do. It's more easy to do something stupid and then find a mistake in this, find a problem with this, and do explicitly. Now we put a filter there, than to just do it the right way in the beginning, because then you cannot write a lot of papers, so you don't get a lot of citations, so you're stupid. Yeah, this is how science works. If you do it right the first time, you don't get the fame. So these things, staggered grids work without filter. The thing is, as I just said, that staggered grids, all nodes are interpolated, and interpolation is a low-pass filter in itself. Okay, officially we have only 5 minutes, but I have always to remind you that officially this is a 3-hour lecture, so I will take my overtime again, yeah, and come to the way that you should actually do it, and this is now the compact interpolation methods on staggered grids, of course. Okay, we have one problem that we want to address, namely that we need quadratic interpolation in order to be consistent with the Navier-Stokes equation. At the interface, at interfaces requires, So, quadratic interpolation requires large stencils, and this is of course a problem. This costs money, it's difficult if you are close to a boundary condition and so on, yeah. So this is not something that you want to have. So the solution to this is we try to reduce the stencil size by using what we have learned about the asymptotic Okay, I know it is very annoying if the professor is dyslexic. So in the first 10 years where I gave lectures, I always thought that I can only use PowerPoint because I mean I'm not able to write things properly, but I decided to do this differently anyway. So we are using asymptotic analysis. We are trying to use asymptotic analysis to get our stencil smaller. So the way we want to do the interpolation is now the following. Let me see again. So take 4. So say this here is in what we call an interpolation cell, yeah, where we put the cell. When I talk about cells, I usually mean, other than other lattice Boltzmann guys, I mean the nodes being at the corners, yeah, not in the center, yeah. So this is because this is what we call an interpolation cell. So it goes from the coarse, it's supposed to go from the coarse to the fine grid. So what we want to do in 2 dimensions is to use these 4 nodes of the coarse grid in order to recover these 4 nodes in the fine grid. Okay. Yeah? And in the reverse, we want to have, let me see, these, oh no, don't draw. We want to use these 4 fine nodes in order to recover 1 coarse node, yeah? So fine to coarse. And we'll call these things here, these are the source nodes, and these are the destination. The destination nodes. So, and now the information that we use for the transfer at the source is the following. So we have to use rho, so the density, we have to use ux and uy. So we are transferring, of course, the macroscopic information, yeah? But we also have to deal with the non-equilibrium part. And the we don't use the entire non-equilibrium part. We only use the one that is required according to second order, according to the asymptotic analysis. And this is M11 and M20 minus M02, right? So these are the things that are required. And the other stuff we reconstruct with equilibrium, yeah? So now according to our asymptotic analysis, we have M11 to second order. This is where which we use for recovering the Navier-Stokes equation. So we'll do this at second order, minus their equilibrium at second order. So the equilibrium can always be recovered from velocity and density, right? Yeah? So, but the non-equilibrium part, which is this, so divided by rho 0, is equal to minus 1 over omega on that particular resolution times theta, and here comes dx uy to first order plus dy ux to first order. And then we have the other one, that is M20 to second order minus M02 to second order minus their equilibrium, M20 equilibrium to second order plus M02 equilibrium to second order divided by rho 0 is equal to minus 2 over omega theta dx ux to the first order minus dy uy first order. Yeah, so this is what asymptotic analysis told us. Yeah, so now first of all we have to transfer these things, but I mean, we have to recover these things when we do the reconstruction. But first, we have to know how to transfer stuff in the first place. Yeah. So, and for this, we use second-order polynomials for the interpolation. So interpolation functions for velocity, yeah. So saying, I say that ux at position x and y, 2 dimensions, right, can be written as a0 plus ax times x plus a y times y plus a xy xy. So now suppose we simply interpolate the velocity. Yeah. So then we have always these 4 nodes. Yeah. So we have 4 information on the node. 1, 2, 3, 4. This is what we can do with just using the velocity in interpolation. Right? But this is not a second order polynomial, even though there is one second order part here. And what we need in order to get a second order polynomial, we need an axx. Okay, let me write this in a different color. Axx x square plus ayy y square, right? So, and obviously for this guy here, we'll do the same and call this b. b0, bxx plus by y plus a, I'm not learning, b xy times x and y plus, so let me use red again. Also here we need b xx x square plus b y square. Yeah, so this is additional stuff that we need to get somewhere from. So for the density we see this is related to pressure, and pressure we only need to have a linear interpolation because we only take the first derivative of this. So then here we'll make our life very simple and say this is c0 plus cx x plus cy y plus cx y xy, so which we call bilinear, yeah? Bilinear interpolation, which we can do just using the density. So now here's our problem. Okay, now, yeah, so we need to have these things. In addition to the velocity, we also have derivatives of velocity, yeah, which we can now use. However, there's a kind of a problem because we have 4 times 4 equals to 16 moments for velocity, I mean including velocity itself and their derivatives. Velocity on these 4 nodes. But if you count the coefficients of this interpolation function, then there will be only 12. So we have an over-specified system. So it kind of does not work out of the box. So what now we have to do is to somehow reduce the data that we have. Yeah? And by the way, the data reduction, the way the data is reduced is so that the data reduction has some low pass properties. Yeah. So it tries to keep as much as possible, but otherwise it filters out higher frequency. Yeah. So we do the data reduction with some kind of a filtered finite difference stencil. Differencing stencil, of which we use two. Say, I mean, we have always 4 nodes, yeah? And say we are using a plus, plus, minus, minus stencil in the y direction and define this as the y derivative. And we use a minus, minus, plus, plus stencil and define this as an x derivative. So we would only need 2 points in order to do this calculation. Yeah. So you can or what you actually do, you compute. So you want to know the finite difference here in the middle. Yeah. So you compute it once left of this point. Yeah, you would end up here, and then you would do it once right at this point, and then you interpolate these twos. Yeah, meaning that you this interpolation afterwards, this has some low pass characteristic.
Okay.
Yeah, so you do twice the you do 2 times a finite difference, and then you just interpolate their result to the point where you want to have it. Yeah. So, and this for M11 would mean that if you apply this, so M11, as you have seen above, is the derivative dx uy. I mean, I take the prefactors out here, yeah, dy ux, and now we take another derivative of this and say we plug into this the coefficients for the interpolation. So we take 2 derivatives, yeah. So, and because we have the second, so what we get out is 2 times bxx plus axy, and we'll take dy dx uy plus dy ux is equal to bxy plus 2ay, and we do the same thing for M20 minus M02, and we apply this stencil, dx ux minus dy uy, and this gives us 2axx minus b xy, and dy dx ux minus dy uy is equal to axy minus 2byy. Right? So, and with this additional information, we are able to determine all the coefficients. Yeah, so because all the other information comes from just interpolating just from the velocity itself. So we get all the information, then of course we have to solve. I mean, I could just give you the answer, but this doesn't. It's not a pretty system. I mean, the result does not look very beautiful. Yeah. So you'll take a computer algebra system and solve this for the coefficients. Then you have the equations that you can plug into your code. We have done this several times in the exercise lately. And then what we do is we are applying this interpolation. Apply this in the interpolation. And then we have, in order to get the velocities at the nodes that we want to have, and we want to have the non-equilibrium part. So the non-equilibrium part we get not by interpolating the non-equilibrium part, which we could also do, but we get it by, we get the non-equilibrium populations from the derivatives of the interpolation function. Yeah, so we know that the non-equilibrium part is made up of these derivatives, yeah, that we just used for the interpolation. Yeah, so this we can calculate directly from the interpolation function. So we take the derivative of this and evaluate them, and so we can recover the non-equilibrium part.
Okay, so because now we know M11 and we know the equilibrium,
so we can calculate the equilibrium. So we calculate the equilibrium from, as usual, yeah, we know the velocity. Yeah, it's important we are not interpolating the equilibrium, but we are reconstructing the equilibrium because, as you know, if you have a high frequency or a signal, which is if you have any signal and you take the square of it, then you will generate double the frequency.
okay.
Yeah, so then you again run into the trouble with the Shannon sampling theorem. So what you do is not interpolating this twice frequency, but only the base velocity. Then you do the square, yeah, and recalculate the function. So first of all the equilibrium, and then also the non-equilibrium from these derivatives. Okay, let's draw these pictures for the equilibrium for the algorithm. Let's look at the algorithm, how this is done. Now I have to, how is the time? Okay, sorry. I have to do some drawing now. So say, you see, I'm doing it wrong again. Okay, we need a little bit of space here. Oh my gosh. Okay, I put the fine grid on the left now, so let's do it this way. So what we are going to do is to use a lot of overlap. So these are 4, 5, 6. We are using overlapping grids, and we have here our coarse grid. Here our coarse grid, and then we'll have the next course here, the next course here, and then we have the next course here and the next course here. So, and I will now say that this is the place where we interpolate to from the fine to the coarse grid, and this here is the place where we interpolate from the coarse to the fine grid. Yeah. So, and in order for this to be possible, we need to have this overlap. Okay? So the step number 1 in the algorithm is that all nodes are known. So we start with everything here is known. Yeah? So then you remember we need to have different time steps on the different grids. This is step 1. So this leads us to step 2. Now I will try to do the following here because I'm an old man and I'm lazy. I try to do this. Can I copy this? And can I paste this? Okay, let's copy and paste this. I don't know whether this makes it non-easy for you. Yeah, but the idea is now we do in the second step, we have a fine time step. So we do a fine time step, and by this we mean that there is no course time step at the same time. Yeah? We only do, now the algorithm does only a fine time step on the fine grid. Yeah? So when we do a time step on the fine grid and these nodes that are on the boundary of this fine domain, they don't have a neighbor. So once we do the streaming, these guys are no longer valid. Right?
Yes.
So then we follow this up with a step number 3. Okay, step number 3, and remember we need two time steps. We need 2 time steps for the fine grid before we can do a 1 time step on a coarse grid. Yeah? So this means second fine time step. Now we have seen that these nodes went out of business last time. Yeah? So they are not able to transfer their usual data to their neighbors. So this means these guys go out of business this time. Yeah? So, and then we have done 2 time steps on the fine grid. Now it's time to do 1 time step on the coarse grid. So this is step 4. This is the coarse time step. So we have seen that on this side, all of them went out of business, and now these guys here have no neighbor, so they go out of business after they have the collision and the streaming. So now all these interface nodes are out of business. Yeah? Comes step number 5, and this is the synchronization step. Means interpolate all interfaces. Or all interface nodes. So, because, I mean, we've seen that these guys here were out of business, right? However, their surroundings are all still in business. So what we now can do is we do interpolation here, and interpolation here. And after this, they will be valid, and we return to step 1. So, and using this overlap also means that there is no interpolation in time required. So instead of interpolating in time, we make use of this overlap. Okay, so this is the compact interpolation grid refinement. So basically this was also the lecture I have. We are not going to do a lot with the code today. I just wanted to announce that there was a mistake. Yeah, so we found some mistakes in the code, and for example, so this, and okay, it was, you observed that the code did not behave the right way all the time, or was a little bit strange. Yeah, so we always had the impression that it worked, but it looked a little bit strange just in a small detail. And take this as a warning, of course. Yeah, never only because it seems to work does not mean that your code is free of errors. Yeah, this is very important. So the error that we had here was that in the boundary condition, this is why it happened all the time. Yeah, so when we wrote the bottom layer, and we wanted to do the bounce back, then it should look like here in the top layer that the bounce back should go from FMM or from FPP to its opposing direction. So from FPP to FMM. And as you see here, we had here FPP coming from FPM. Yeah? And also here. So there was this, and mistyping, yeah, and this was copied all the time because we did not touch it and did not change it. This was one difference. Another difference that I made in the code was then at least for the cumulant method. I think in the one that I uploaded, I did it only for the cumulant method. Maybe this is the one that is correct. This is the one that's corrected. I also put the lid, the driving lid, in the corner. Yeah, because this made a little bit of a difference at this very high Reynolds numbers. Yeah, so we can, just for the fun of it, I now did not use a very high Reynolds number, I believe. Let me see. Okay, I put it to 1.996. I'm using cumulants, and I'm using the third order moments with a or cumulants, the third order cumulants with an under relaxation here. This is something that we'll discuss in the last lecture in 2 weeks. That it is actually known that the third order moments need. I mean, you get higher accuracy if you match the third order, the relaxation rates of the third order. if you under-relax them, you actually have to under-relax them in a specific way, which I've not taken care of now, because this is a little bit complicated. So this is something that we talk a little bit about in the last lecture. So the next lecture in 1 week we'll talk about implementation details. So what you need to take into account to have an efficiently running code. So the code that we've wrote here is not necessarily a code that we would recommend to write it this way, because it's not necessarily an efficient code. It's just plain, written down. Okay. Yes. So I'll stop the recording. Thank you for attending.